Watch it. 3, 2, 1, 0. There it goes. And I will stop it. The current is still going. That is the equilibrium position. And I will stop the current. And now I will reverse the current in the opposite direction. And now you will see that it swings backwards. It's 180 degrees in a different direction. 3, 2, 1, 0. There it goes. I will stop it. A few seconds, that's the equilibrium position, and I let it go. So you've seen that indeed the magnetic needle responded to the magnetic field that was produced by the wire. This was the great discovery by Ørsted. The discovery, this demonstration all by itself, may not be very spectacular for you, but historically it is of enormous importance. I would argue perhaps the most important demonstration, the most important research ever done in physics, because it connects electricity with magnetism. It was the foundation of the creation of the whole concept of a field theory. Action equals minus reaction, and that means that if a wire that runs a current has a force on a magnet, then of course the magnet must also exert a force on the wire. And I'm going to demonstrate that to you too. But now I have a much more potent magnet, for which I will use this one. And the magnet will not move. It's so heavy that it can't move. So now you will only see the wire move. And the basic idea is then as follows. Here is that magnet. This is the north pole of the magnet. And this is the south pole. I don't remember which is which, to be frank with you. So the magnetic field would run then like so. And I have here a current wire, a wire that runs a current through it. The wire is perpendicular to the blackboard. If, when I turn the current on, if the current is coming out of the blackboard, and I have 50% chance, because I really don't remember whether this is north or south. But let's assume that this is the configuration, that the current is coming out of the blackboard. Then you will see this wire experience a force up. It is an experimental fact that the force on the wire is always in the direction of I cross B. These are unit vectors. And since I is coming out of the blackboard, if I cross I with B, I get a force in this direction. And so if I reverse now the current, if the current goes like this, then of course the wire wants to go down. And I will show you both. But I don't know which one will come first, because I didn't mark the poles. Oh! So you'll see it now slightly different from the way I have drawn it. I've drawn you the magnet looking this way, but it's of course much nicer for you to see it this way. So you see the wire, and there is the magnet. And now I'm going to run a few hundred amperes through that wire, and then it either will jump up or it will jump down, and then I will reverse the current, and then the opposite thing will happen. Okay, we ready for this? 3, 2, 1, 0. Notice there was a distinct force down. The force was so high that it even pulled down the supports. So now I can predict that if I reverse the current from this experiment, that now the wire will jump up. There we go. I know now exactly because I switched it this way, so now I will switch it this way, and the wire will jump up. That's the first drawing you see. 3, 2, 1, 0. Very clear. You saw it come out. Okay. You take this down. All right. If I have a wire through which I run a current, let's say I run a current I1 through this wire, it will produce a magnetic field, right-hand corkscrew, right here. That magnetic field will be in the blackboard. I'll call it B1. Right here, it will be out of the blackboard. But that's irrelevant right now. But it is out of the blackboard. Here it's in the blackboard. And here, I have another wire. I'm going to run a current I2. There will be a force now on this wire in the direction I cross B. Take your hand, I cross B, that force is up. So this wire will experience a force up. But of course, if this wire experiences a force up, since action equals minus reaction, this wire will experience a force down. So they will go towards each other. They will be attracted by each other. You can in an independent way confirm that the force here is down. So this is the force. For me, it would be enough to say action equals minus reaction, Newton's third law. But if you want to put in here the magnetic field B2, which is the result of this current, which is, of course, out of the blackboard, remember the right-hand corkscrew rule, then you will see that this force now here must be in the direction of I1 cross with B2, and that's down, which is exactly what I predicted. So the two wires will go towards each other. However, if I leave everything the same, but I reverse the direction of I2, so now the two currents are in opposite direction, then the forces will flip over, and so now the two wires repel each other. And I will demonstrate that to you. I have those two wires here, and you will see them there on the screen. I will explain what you're looking at in some detail. The two wires run vertically. This is one wire, and this is the other wire. And when I run a current in the same direction, then they will attract each other. And you will see that shortly. 3, 2, 1, 0. See, they go towards each other. I will do it again. Now, if I run the currents in opposite directions, they will repel each other. Now I run them in opposite direction. They repel each other. I'll do it again. 3, 2, 1, 0. They repel each other. The reason why I showed you this demonstration is a different one. What I want you to appreciate that if I have this conducting plate of aluminum, it's a conductor, and I put that in between the two wires, and I repeat the experiment, that exactly the same thing will happen. And that tells you that magnetic fields are really very different from electric fields, because electric fields would be heavily affected by a conducting sheet like this.